So first we'll use the measuring tape to measure our distance from us to the tree itself. So using the measuring tape, I found that the distance between me and the tree was 127 feet. Now you don't need to use the measuring tape. If you're comfortable with measuring distance via your own pacing, you can do that as well. My pacing is 5.5 feet for every one pace, for instance, and that would give me 127 feet as well. So again, we need to measure the horizontal distance between us and the tree, and the ground distance is part of that equation. We need to once again consider the right triangle and the fact that our ground distance between us and the tree is the same as the hypotenuse of that right triangle. The distance, the horizontal distance between us and the tree, again its trunk extended into the ground, that straight line distance, that horizontal distance, which is impossible to measure directly, we need cosine, the cosine function, in order to determine that distance. So consider the right triangle and the cosine function itself. In a right triangle, cosine of theta, our angle of elevation in this case, is going to be equal to adjacent side over hypotenuse. That adjacent side is going to be equal to our horizontal distance. That's what we need to determine. Cosine of theta equal to horizontal distance over hypotenuse, or ground distance. So we've measured that ground distance, we've measured that hypotenuse. So now we need to measure our angle of elevation. And that's where the clinometer comes in again. We're going to use the clinometer to measure that angle of elevation. Looking through the viewfinder, we're going to use the left-hand scale, which is the degree scale. So a few words about that angle of elevation. I want you to consider for a moment where that angle resides. It's actually formed by the lines of our hypotenuse and our horizontal distance that again is going to go underground, looking straight ahead, if that trunk of that tree were to extend all the way into the soil. Where those two lines meet is actually down here at the ground. So one could argue, well, don't you need to get down on the ground to actually measure that angle? Well, no, we can keep things comfortable. We're still going to use the clinometer next to my eye standing up. So we need to account for that by actually focusing on a portion of the tree where your head would be if you were standing next to the tree. And to make things easy for me, I've placed an orange flag up on the tree where my head would actually reside if I were standing next to the tree. That way, as I'm pointing up at that target, I'm paralleling the ground. I'm paralleling that straight line formed by the ground if we were to walk up to the tree itself. So that allows you to remain comfortable as you take that reading. So again, looking through the viewfinder, we're going to use the left-hand scale. And if you're looking at the degree scale, first thing you do is zero out the scale itself. So you have that black horizontal line, line up the 0 with that line. And that's going to mean you're pointing right into the ground itself. So then you slowly move the clinometer up until that black horizontal line intersects with your target. And in my case, it's that little orange flag that I placed on the tree itself. If I were standing right up there at that tree, there would be an invisible line connecting my head to that flag. Read the degree scale at that point, and we find that we have an angle of elevation of 15 degrees. So in terms of our right triangle, in order to determine that horizontal distance, we need to use the cosine function. So cosine of our angle of elevation is equal to horizontal distance over hypotenuse, or ground distance. Horizontal distance over ground distance. We've determined that ground distance. That's 127 feet. Our angle of elevation is 15 degrees. So cosine of 15 degrees is equal to horizontal distance over ground distance. So in order to determine what our horizontal distance is, we'll be multiplying cosine of 15 by 127 feet. So cosine of 15 degrees, how do we figure out what that is? Well, that is another reason that the clinometer itself is a handy tool, because right on the side of the clinometer is a cosine table. It gives you cosine of certain angles, anywhere from 1 degree to 45 degrees. So you can use your clinometer on most slopes. Even if you don't have the angle that you want on your clinometer, there are cosine tables that you can look up on various math websites. So what we need is cosine of 15 degrees. So looking at my clinometer, cosine of 15 degrees is 0.9659. So we plug that into our equation. Cosine of 15 degrees equal to horizontal distance over ground distance. In order to find horizontal distance, we multiply 0.9659 by 127 feet. So working out that multiplication, 0.9659 times 127 feet is equal to 123 feet. So our horizontal distance, that distance between us and the trunk of that tree, if it were to extend all the way into the soil, is 123 feet. So to go back to the very beginning of this module, anytime you're measuring tree height, you need two vital pieces of information. And what are they? You need your horizontal distance, and you also need your percent reading from the percent scale of the clinometer, because the tree height is going to be a certain percentage of your horizontal distance from the tree. We've determined our horizontal distance, so now the last thing that we have to do is use the clinometer's percent scale to figure out what portion of that percent scale is occupied by our tree. So let's take our percent readings. Using the clinometer's percent scale, if I focus on the bottom of the tree, I have a percent reading of 23. Next thing I do is focus on the leader, the very top of that tree. The percent scale for the very top of the tree, the leader, is 65%. So what do I do with those two numbers? 65% and 23%. Well, I subtract them from one another. The portion of the percent scale occupied by my tree is 65 minus 23, or 42%. So our percent scale reading is 42%. In order to work with that number, we need to convert it to its corresponding decimal. So we divide by 100. So instead of 42%, we have 0.42. So we have all the information we need. The height of this tree is equal to our percent reading, 0.42, multiplied by our horizontal distance from the trunk of the tree itself, if it were to extend into the ground. Horizontal distance multiplied by your percent scale reading. So in that case, we have 123 feet multiplied by 0.42, 0.42. And that winds up being 51.6 feet. Round that to the nearest foot, 52 feet. So this tree is 52 feet high. So let's distill things a bit. This was a rather protracted way of describing how you determine tree height, especially for trees found on a slope. But what we did is very simple. We found out our distance from ourselves to the tree itself, walking up slope, measuring that ground distance. You're going to do that all of the time. You're going to capture your percent reading from your percent scale. That's the same regardless of where your tree is located. Level ground, on a slope, measure the distance between you and the tree, and take in your clinometer percent reading. However, when you're working on a slope, you also need to figure out your angle of elevation or angle of depression and take the cosine of that angle. So, put simply, the factor that you need to multiply by anytime you're on a slope is cosine of your angle of elevation or depression. That's what you need to factor in anytime you're working on a slope.